Dear learners of control systems, I welcome you to the presentation on Type 1 second order system MATLAB simulation. In the last video, that is my third video, we have explored the step response of Type 1 first order system by MATLAB simulation. So here we are going to see the simulation of Type 1 second order system. So to understand this better, I want you people to go through theoretical explanation for the same. That is, you go to the Dr. C. Ganesh teaching modules. So in that there is a playlist. So in that playlist, control system lecture series is there. In the control system lecture series, lecture 6, time response of second order system. In this, I have theoretically given explanation for the time domain specifications with respect to the step response of a type 1 second order system. I hope you can go through that and gain confidence on the step response of the second order system theoretically, right? So with that confidence, if you come to this particular video, or if you proceed with this video, definitely you will be able to understand the MATLAB simulation better. So now let me go to the MATLAB simulation. So obtain the step response of a unity feedback type 1 second order system whose open loop transfer function is given by g of s equal to 100 by s square plus 10s by MATLAB simulation. So s square plus 10s means it is s into s plus 10. Actually, it is s square plus s 10s can also be written as s into s plus 10 in the denominator. So if we have one s at origin, that is one pole at origin, or one s factor in the denominator of the open loop transfer function, we call type 1 system. Like the previous one, that is the type 1 first order system, we had 1 by ts. Since it was a first order system, the type was also 1, order was also 1, since you had only one s in the denominator. However, here type is 1, order is 2, because s square is the highest power of s in the denominator. Right. Now we need to understand how the rise time, peak overshoot, settling time, and steady state output are affected due to the damping. So theoretically, we can actually do the step response. This is of the form omega n square by s square plus 2 zeta omega ns. You can refer my video that I have already said in the beginning in the control system lecture series. So there I would have given the theoretical explanation, analytical explanation for doing this time domain specifications from the mathematical point of view. Now we are going to see the simulation. So omega n is 10 radian per second. Here you can see. Then 2 zeta omega n is 10. Therefore, from that zeta can be taken. And what is the damping ratio? We are going to see now. So the damping ratio will be actually 0.5. So 2 into 0.5 into 10 is 10. So let us check this by MATLAB simulation. Right. So I am writing the program NUM 100. S square plus 10s. Therefore, I should have in the denominator 1 as the first term, 10 as the second term, and there is no constant term, therefore 0. Therefore, this will be s square plus 10s plus 0. So I am assigning this numerator and denominator to forward part transfer function. Feedback part transfer function is 1. I am going to use the keyword feedback as usual. Sys for sysfeed, like how we have done in the earlier two videos. Then I am going to simulate the step response of the system. Now I am going to copy this and then paste it in my MATLAB simulation video. MATLAB simulation window. So here this S is lower case, right? So I am just running this. So if you run this, you will get the response. Before that, you want to check what is the forward part transfer function. So you type sysfor in the command window. So you have to get 100 by s square plus 10s. Yes, that is what we have got. 100 by s square plus 10s. Correct? Therefore, let us explore the step response. That is, we see the characteristics. Let us check rise time, then we need to check peak response, then we have to check settling time, then the steady state value. So if you check the rise time is actually the rise time 0.164 second. Right, let me check it out. Yeah, 0.164 second. 0.164 second. So is it 0.16? Let us check in the word file. Then the peak time is 0.359 seconds. So this is peak time means the time taken by the system response to reach the peak value of the response. So when I move this, yeah, 0.359 second, and the overshoot is 16.35. Then the settling time 0.808 second, and the final value is 1. So these are all available in the step response that I have shown here. So rise time is 0.164 second. I think I have indicated that in the MATLAB window. Overshoot is 16.3%, and 0.36 second is the peak time. The settling time is 0.808 second. Final value 1, that is steady state value is 1. Anyway, this you can theoretically check it out based on my control system lecture series. There is step response of type 1 second order system, that is video 7. You can refer and then you can check it out using the formula. Right, that is one thing. Then now what I have done is the second system is 100 by s square plus 20s. So here I have actually changed the damping ratio from 1 to 2 because omega n is 100 only, but the damping ratio here it is 1 because 2 zeta omega n is 20. Therefore 2 into 1 into this 10, omega n square is 100 means omega n is 10. Therefore 2 into 1 into 10 is this 20. Therefore the damping ratio is 1. Therefore critically damped system. Now what I have to change in the MATLAB window, I should just change the denominator into 20, that's all. Nothing else I have to change. So I am running now. So when I run this, I get a different response. There is no oscillation. There is no oscillation. And if you check the forward part transfer function, if you check the forward part transfer function, so it shows 100 by s square plus 20s. Because 100 by s square plus 20s only I have shown in the word file. Now, the closed loop transfer function and all that you can check it out. That you will get correctly only. That is 100 by s square plus 20s plus 100. Right, that's a different thing. Now we will see the characteristics. So I am just putting the right click, rise time. So the rise time is 0.336 second. Then the peak time is greater than 0.8 second. So there is no overshoot, right? Overshoot is 0 because it is critically damped. Then settling time, if you see the settling time is 0.583 second, and the final value is 1. So these things I have copied and pasted here. Yeah. See, the rise time is 0.33 second, 6 second. Then settling time, anyway, I have not plotted the peak time. Settling time is 0.583 second. Final value is 1. So, rise time is 0.164 in a underdamped system. when the damping ratio is 0.5. Now the rise time is increased. Therefore, increasing the damping ratio results in increase in rise time. That is what we have seen theoretically. Then, when you increase the damping ratio, overshoot is reduced. There is no overshoot at all now because it is critically damped. But settling time 0.808 second, now it is 0.583. So there is slight reduction in the settling time. Okay, it may appear that this settling is comparatively smaller than this. But if you go for a overdamped system, probably things will be different. For example, I am going for overdamped system. See, denominator I am putting 100. That is 100 by s square plus 100s. So omega n is 10. 2 zeta omega n is 100. Therefore, zeta is 100 by 2 into 10. That means the damping ratio is 5 over damped system. Therefore, what I should do here, 20 must be changed into 100 and I have to run. I should run. Now I have run. Of course, you can check those things. SYS for you can check. That is forward path transfer function. So forward path transfer function, if you enter, so it will give 100 by s square plus 100s. That's fine. Now let us go to the right click and then check the characteristics. So characteristics, peak response. So peak response is more than 6 seconds. Overshoot 0. That is not a matter because it is a overdamped system. So rise time. So rise time is 2.17 seconds, much higher compared to the even critically damped system. Then what about the settling time? So settling time is 3.88 seconds. So what about the final value? Again 1 only. So steady state value is 1 only. So these things were plotted separately into the MATLAB, from the MATLAB file into the Word file. So whatever I said, rise time 2.18 seconds, settling time 3.88 seconds. This is for overdamped system. Now I am consolidating all these and putting in the inferences under the result. So in the first case, when the open loop transfer function was 100 by s square plus 10, the damping ratio was 0.5. Then undamped natural frequency of oscillations omega n is 10 radian per second. Then rise time is 0.164 second, peak time 0.36 second, overshoot 16.3% peak overshoot, settling time 0.808 second. There is steady state output 1. That means there is no steady state error. So system is underdamped. And when you increase this 10 into 20, this is actually s square plus 10s. So what happens is the damping ratio is 1. So from 0.5 the damping ratio is increased to 1. Omega n remains at 10 only, but rise time is increased, settling time has slightly reduced, steady state output is 1. And when you increase the damping ratio further by increasing the coefficient of s, what happens is, that is omega n is 10 only, but zeta damping ratio is 5. But the rise time 0.164 to 0.336 to 2.18 increase. That is when you travel from 0.5 damping ratio to 1 to 5. Whereas the settling time, if you see, from 0.5 to 1 there is slight decrease. But from this to when you see the critically damped to overdamped, the settling time is 3.88 seconds. So therefore, the rise time is more, settling time is also more. That is why critically damped system, that is overdamped system, they are generally slower. So overdamped systems are slower. So the response is sluggish. That is why they find less applications. Where oscillations cannot be tolerated, in those applications only one can use overdamped systems. So that is why overdamped systems are seldom used. So this point we have stressed in Lecture 7 in the lecture series, control system lecture series in Dr. C. Ganesh Teaching Models YouTube channel. The same thing I am just reproducing it but with the help of MATLAB. So I hope you have understood that MATLAB is a powerful tool for understanding the behavior of the first order system or second order system or any control system. So if you have any doubts, probably you can go through that video and come back here. Thank you.